Okay, yeah, let's go ahead and get started. All right, so we've been talking about collision experiments. I mentioned a little bit about how the collision experiments can be used to obtain potential energy surfaces for the interaction between molecules or atoms. And so today we're going to start by talking in more detail about potential energy surfaces. What does that mean? How do we use them? Okay? So the topic is potential energy surfaces. And the concept of a potential energy surface is really central to the way that chemists think about problems, right? The zeroth order picture that a chemist always has in his or her mind is a potential energy surface that describes the energy as a function of the nuclear coordinates. But it's actually not completely obvious that these potential energy surfaces that we use all the time, that they're a good description of reality, right, of chemical dynamics, because they rely on an approximation called the Born-Oppenheimer approximation. And this approximation is so central to the way that most of us think about chemistry that sometimes we forget that we're even making this approximation. We, as chemists, we just always sort of have this in our mind. But basically, the Born-Oppenheimer approximation says that the mass of nuclei are at least 1,000 times heavier than the mass of an electron, and so therefore the electrons are moving much, much faster than the nuclei, so that when you solve the Schrödinger equation for the electronic wave function, you can ignore the motion of the nuclei. That's essentially what the Born-Oppenheimer approximation is saying. Okay? And so if we write the total Hamiltonian for some chemical system, for today, I'm going to ignore the effects of spin, right? So I'm not going to include spin-orbit coupling terms, but I'll include everything else. But the total Hamiltonian H total, we could write this as a sum of terms. So for all the nuclei, we have to sum over each nucleus, and we need a term for the kinetic energy of the nucleus. And we have to sum over all the electrons, and we get a kinetic energy for each electron. Right, and then, so that's the kinetic energy part of the Hamiltonian, then we need the potential energy, and so we have electron-electron repulsion, and we only include the repulsion of each pair twice, so I'm going to sum over the electron indices I and j, but only for I less than j, so that we don't double count the repulsions. And then we need an E squared over the distance between the nuclei. Okay, and then, so that's electron-electron repulsion. Then we get a electron-nuclear attraction term, where we sum over every electron I and every nucleus N, and we get the atomic number of the nucleus, right, times the charge squared. And then we divide by the distance between the electron and the nucleus. Okay, and then we need one more term, and that's the nuclear-nuclear repulsion, 1 over 4 pi epsilon naught. Okay, here we sum over all the nuclei, n less than n prime. let's say, and we multiply the atomic numbers, and then times the charge, elementary charge squared. Sorry. Okay. So these are probably sorts of terms that you've seen before. Okay, but we can write this in a simpler way. We can just call this the kinetic energy operator for the nucleus plus the kinetic energy operator for the electrons, right? This one, plus the electron repulsion potential operator plus the electron nuclear attraction operator plus the nuclear repulsion operator. Okay? And so because you have moving electrons and moving nuclei, and they're interacting with each other, in general, the electron coordinates, which I've been denoting as little r, right, and the nuclear coordinates, which I've been denoting as big R, they are not separable. In other words, you cannot write the wave function as a product between a function of little r times a function of big R. Okay? But, like we've said, the nuclei are moving much slower than the electrons, and so maybe we can find an approximation where they're approximately separable. And so that's the approach of the Born-Oppenheimer approximation. So in the Born-Oppenheimer approximation, we define what's called an electronic Hamiltonian. And the electronic Hamiltonian includes all these terms except for one of them. If we get rid of one term, we make our lives much simpler, and that is we get rid of the kinetic energy operator acting on the nuclei. So basically we ignore nuclear motion, right? So the electronic Hamiltonian is simply equal to the total Hamiltonian minus Tn, right? The nuclear kinetic energy operator. And if you're including spin orbit effects, you would also subtract the spin orbit operator. But I'm going to leave that out for today for the sake of simplicity. Okay, and so this operator then, the terms that we're left with are kinetic energy of the electrons plus all these interactions. The electron-electron repulsion, electron-nuclear attraction, plus nuclear-nuclear repulsion. Okay? And so basically, within the Born-Oppenheimer approximation, the approach that we're going to follow basically separates the problem into two steps. So the first step in our approach, we're going to find eigenfunctions of the electronic Hamiltonian for fixed values of the nuclear coordinates. Okay, so basically you clamp the nuclei in place. Okay? And so we can write that as follows. We have this electronic Hamiltonian. It depends on the electronic coordinates, but it also depends parametrically on the nuclear coordinates, right? If you change the nuclear coordinates, you get a different system of clamped nuclei, and you get a different electronic wave function. Okay? And then this operates on a wave function, which is a function of the electronic coordinates, but it's also parametrically defined as a function of the nuclear coordinates. And so this semicolon here means it's a function of little r, but it's parametrically a function of big R. So big R is a constant, but if we change that constant, we get a different wave function. Okay, and so we solve the time-independent Schrodinger equation to get some energy, which is going to be a parametric function of big R times psi. Okay, and if you've ever done a electronic structure calculation in Gaussian or whatever your favorite package is for doing electronic structure calculations, this is what you're doing. You're solving this equation. You're clamping the nuclei in a particular position, and you're solving for the eigenvalues and eigenfunctions of this time-independent Schrodinger equation, which ignores nuclear kinetic energy. Okay? So you can repeat this process for a lot of different values of the nuclear coordinates. And then, okay, so just for simplicity so that we can draw a simple graph, let's just assume we have a diatomic molecule with only one bond length, right, R. So we can obtain then EI as a function of R. And at different points R, we get different values of energy, right? And then we can draw a smooth curve between all these points that we calculated, and then we get a potential energy surface. But depending on the method that you're using, you can also calculate not only the ground state energy, you can also calculate higher lying wave functions. And so for each point R, you could also get, for example, the first excited state, right? So let's say the first excited state at each point looks like this, right? So then you get one potential energy surface for the ground state, one potential energy surface for the electronically excited state, and so forth. You could calculate higher states as well. Okay? And so these values that you calculate here, and which are plotted here, these are the potential energy surface. That's what we mean when we say potential energy surface. Okay, so that was step number 1. Step number 2 is after obtaining the electronic potential energy surface, we solve for the nuclear motion on that surface. So we solve to obtain a nuclear wave function. Well, I'll call that chi of R on the ith potential energy surface. Okay? And so explicitly what that means is we take a time-independent Schrodinger equation. It's going to have the form of, we take this E sub I of R, right? This is the potential energy operator. And then we add the nuclear kinetic energy operator, and the wave functions and eigenenergies have to obey the time-independent Schrodinger equation. So this operator acting on the nuclear part of the wave function has to equal the energy times the wave function. Okay? And so in general, this is an approximation, but the Born-Oppenheimer wave functions, right, the electronic wave functions that you get and the nuclear wave functions that you get, they form a complete basis set. So you can always write the real wave function, which is the eigenfunction of this total Hamiltonian. You can write it as a linear combination of the Born-Oppenheimer wave functions. So the real wave function, I'll write that as a capital psi of, and this depends on the electronic and nuclear coordinates, not in a parametric way, right? But it's really a function of a wave function of both sets of coordinates, right? You can write this as a linear combination summing over k and I of some coefficient AKI times the Born-Oppenheimer nuclear wave function times the Born-Oppenheimer, how have I denoted this? Psi? Yeah, psi r semicolon big R. Okay? Okay, and so then the Born-Oppenheimer approximation essentially amounts to assuming that only one of these coefficients is non-zero and all the other coefficients are zero, right? So you only have one electronic state and one, vibrational wave function on that one electronic state, right? If the Born-Oppenheimer approximation is not a good approximation, then you have a wave function that is a linear combination of nuclear wave functions on multiple different electronic states, right? And then your life gets complicated because you no longer can consider just dynamics on one potential energy surface. You have this complicated situation where the nuclear and electronic motions are coupled to each other and you can't separate them. Okay? So let me go over here so I have a little bit more space. Okay, and so now we're going to consider matrix elements of the Hamiltonian in the Born-Oppenheimer basis. So okay. So basically, I'll denote this H, K prime, I prime, Ki, right? And so a matrix element, that means you take basically the K prime, I prime wave function state, and you take an overlap integral where you act the Hamiltonian on one state in a ket, but another state in a bra. Okay, that's just what I mean when I say matrix element. Okay, and so for the problem at hand, if we write this out explicitly, in the Born-Oppenheimer basis, we have these product wave functions, right, of a nuclear times an electronic part. And so I can write psi I prime, right? This is the electronic part. Yeah, and so for now, I'll write it explicitly what it's a function of times a vibrational part. So the kth vibrational wave function in the ith electronic state. This is a function of big R. Okay, and then our full Hamiltonian is the electronic Hamiltonian plus this nuclear part that we removed earlier. And then as the ket state, we get the same thing except with K and I instead of K prime and I prime, right? So we're just taking a different state, Ki. So I can write that as chi Ki of big R times psi Ki of little r semicolon big R. Okay? So just to make this a little bit simpler, I'm going to drop all the r's and I'll just keep the psi's and the chi's. right? The electronic wave functions and the vibrational wave functions, or nuclear wave functions, I guess I should say. This could also include rotation, translation, etc., any nuclear motion. Okay, so the way that we've defined these wave functions, what's going to happen if we operate the electronic Hamiltonian on this wave function? Yeah, so this wave function was obtained by solving this eigenvalue problem, right? So this wave function, by definition, is an eigenfunction of the electronic Hamiltonian. So when we operate on this Born-Oppenheimer basis electronic state, we just get the electronic energy, the Born-Oppenheimer electronic energy of that state, which is defined parametrically as a function of r. So psi I prime, chi k prime I prime, right? Then we operate this on this state, we're going to get the electronic energy of the ith state defined parametrically as a function of the nuclear coordinates. Okay? And then plus we get this nuclear operator. I'll write this a little bit more explicitly. The nuclear operator is, or the nuclear kinetic energy operator is minus the sum over all the nuclei of del squared, right? Nuclear second derivative with respect to nuclear coordinates of the wave function over 2 times the mass of the nucleus. Okay? And then this is still operating on chi ki psi. Actually, I don't need a k here. Psi I. Okay? So now, this thing, right, it's operating on this product wave function. And so, now we have a situation where actually, right, so like only this guy depended on the electronic wave function, or on the electronic coordinates, so we were able to operate this electronic Hamiltonian only on this part, it doesn't operate on this part. But now we have two things, they both depend on big R, right? Because this one is a function of big R, this one depends parametrically on big R. And so we have this del operator, this is like a derivative operator with respect to big R. And so so basically this is like a second derivative. When you apply a derivative operator to a product of two things that both depend on the coordinate with respect to which you're doing the derivative, you have to use the product rule. So if this were a single, if it were a first derivative, right, you'd get the derivative of this function times this one plus this function times the derivative of this one. But this is a basically a second derivative, so you have to apply the first derivative using the product rule, then you have to apply the derivative one more time, again using the product rule. And if you do that, what's going to happen is you're going to get, basically, you're going to end up with three terms, one involving the second derivative of this function times this one involving this function times the second derivative of this function, and then you get one more term where you have the mixed derivative, where you get the derivative of this one times the derivative of this one, right? You actually get that one twice, 2 times. Okay, does that make sense? I'm not going to do that all explicitly because it'll take too long, but you can work through the steps on your own and check that I've done it correctly. So it's going to give us 3 terms. So the first one is where we take the second derivative of this guy. Okay, so we ignore this one, we just apply this operator to this term. Okay, so what's that one going to give us? How do we define, or how did we obtain this nuclear wave function? Right? Yeah, so if we apply this operator to this nuclear wave function, the way that this is defined, we obtain this nuclear wave function by solving this time-independent Schrodinger equation. So it is defined as the eigenfunction of this operator. And so therefore, the first term that we get, where we just apply this operator to this first term, that's going to give us just this EIK, right? And then we're going to get the same wave function back again, and then we multiply it by this wave function. And so it's going to be most of the time 0, right? Because these are orthonormalized basis functions. So if I prime is different than I, this overlap is going to give us 0. So it's only going to be non-zero.
Delta.
Yeah, if I prime is equal to I. Right? And if you've written the vibrational or the nuclear wave functions such that they are also eigenfunctions, right? You've already taken care of all the anharmonicity and stuff like that. You're also going to get the delta k prime k, right? It depends on how you've done your treatment. Maybe you haven't diagonalized the vibrational part of the Hamiltonian yet, so maybe you don't have that delta. But anyway, yeah, I mean, we can go ahead and assume that delta k prime k. Okay. So that's the first term you get. Then you get, as a second term, we'll take the mixed derivative. So we get one factor of del operating on this guy, one factor of del operating on this guy. Okay? And so that's going to give us a second term minus sum over all the nuclei of 1 over m, mass of the nucleus. We actually get 2 of these mixed derivative terms, right? So that gets rid of a factor of 2 in the denominator. And then we're going to get 2 matrix elements, one for the nuclear part of the wave function, and one for the electronic part. Okay, and then we get a third contribution operating this del squared operator where both of the derivative operators operate on the second wave function here on the electronic part. And that's going to give us minus sum over all the nuclei 1 over 2mn times this thing that looks like a Frank-Condon factor, sort of, right? This is a vibrational overlap between vibrational wave functions in different electronic states, so it's not necessarily 0. And then we get an electronic part. Okay? And so we can sort of think about these 3 different terms. This one, this is just the result of the Born-Oppenheimer approximation. So if the Born-Oppenheimer approximation is valid, then this is the matrix element. It's diagonal in the electronic states. There's no mixing of different electronic states. You just get total energy, right? The electronic plus the nuclear energy. Okay? This one, in most cases, fortunately, is very small. So most of the time, this third term, you can ignore it. However, this one can be pesky sometimes. And this leads to what I'm going to call non-adiabatic interactions. So this one can mix the different electronic states. And we can think about, when is this term going to be significant? Right, so you have 2 factors multiplied times each other. So both factors have to be significant in order for this to make a significant contribution. So the first factor is a nuclear momentum operator operating on the nuclear wave function. And so if you have slow nuclear motion, right, small momentum, then you're going to have a wave function that varies very slowly with nuclear coordinate. It's going to be small contribution. But if you have a highly excited nuclear wave function, right, high V state, then you're going to have a wave function that's oscillating rapidly with respect to the nuclear coordinate. It's going to have a very high derivative on average, and it's going to make a large contribution. Okay, so you have to have fast nuclear motion, right? Fast nuclear momentum, high momentum of the nuclei. And then it's multiplied by the second thing. The second thing is maybe a little bit weirder looking because we're taking a derivative of the electronic wave function, but with respect to the nuclear coordinate. So the second thing says that the electronic wave function has to be changing quickly with respect to movement of the nuclei. Okay, so I move the nuclei just a little bit, and the character of the electronic wave function changes dramatically. So if you're in this kind of situation, then you can have these interactions between the Born-Oppenheimer electronic states. Okay, so when the nuclear momentum, I should say rather, is large and electronic wave function changes rapidly with the nuclear coordinate r, then the Born-Oppenheimer approximation breaks down. Okay? And the Born-Oppenheimer approximation, in most cases, is actually a very good approximation. It's really, really valuable. It gives you very close to the real picture. But sometimes, in some regions of the potential energy surface, it can break down. And that's most likely to happen when you have two electronic states that come very, very close together in energy. And so I'll give you an example of one situation where that might happen, where you have two electronic states that are crossing each other. So if I draw the energy as a function of nuclear coordinate, let's say I have a system where I have two atoms that come together and they do a charge transfer, right? So I'll draw it. First, I'll just draw it, and then I'll sort of explain what I've drawn. Okay, so here you have the m plus x minus surface. Here you have m plus x minus, and then here you have the mx surface, or m plus x. And here is mx. Okay, so basically you have, so the lowest energy of the system, when you have separated atoms or separated molecules, is neutral, but then when they come close together, then the lowest, at some point these two potential energy curves cross, and at close distances they like to transfer an electron, right, from the, maybe this is a metal, this is a halide, right, and you get an m plus x minus charged species at close distances. Okay? And so these curves that I've drawn here, these are called diabats. These are not the curves that you get if you solve for the energy of the system using your Gaussian program. If you use your Gaussian program, you just get basically two energies, the ground state of the system and the excited state of the system. So you're going to get two potential energy surfaces. One is going to look like this. So it's going to pretty much follow this diabatic curve that I've drawn. But in this region where they're close together, there can be interaction between the two states, which can lead to an energy splitting. Right, and then if you obtain the excited state, energies, basically it's going to look like that. So these things are called adiabats. Okay, and if the Born-Oppenheimer approximation is good, then the system is going to follow the adiabats, meaning you come in with m plus x, you cross this region, there's an electron transfer, you end up with m plus x minus. Right, or if you're on the first excited state, you just, you would have mx with no charge transfer at short distances, but you're going to go to m plus x minus at large distances. Okay, so basically why does the Born-Oppenheimer approximation break down here? Well, assuming that the nuclei are going fast, right, so that this first condition is met, this first thing is large. The second thing, in this region, it's going to be large because as you change r over this region here, next to this crossing, you have a large change in the character of the electronic wave function, because you go from having a electronic wave function where the electron's on the metal, but then you move just a little bit, and the character of the wave function changes completely, where the electron hops over to the halide. Right? So does that make sense? And so if you cross this region really slowly, then the non-adiabatic interaction is going to be small, and you're likely to stay on the same adiabat. But if you cross this region with a large momentum, then both this term and this term are going to be large. You're going to have strong coupling between these two different electronic states that you calculated with your Gaussian program, and then you actually have the ability to do something that you wouldn't predict by the Born-Oppenheimer approximation, which is you can jump from one adiabat to the other as you cross the crossing region, and you can actually follow this solid line diabatic curve. Okay, does that make sense? Okay, so that is the Born-Oppenheimer approximation in a nutshell. Oops. Okay, and so maybe my battery's dead. Okay, doesn't matter. I can just draw it on the board. Oh, right? No. Okay, never mind. Okay, laptop's not working. Sorry about that. Okay, so we sort of drew some simple potential energy surfaces for just diatomic systems. Of course, as you increase the number of atoms in your system, the potential energy surface starts to become much more complicated because you have 3n minus 6 vibrational degrees of freedom in your system. And so, for example, if you have a triatomic system, right, we can consider the potential energy surface for this reaction that we've been talking about, F plus H2. If you have a triatomic system, then let's see, I have to think about this. We're going to have, let's call this one RHH, and this one RFH. And the way that this potential energy surface looks is kind of like this. So basically, this is drawn as a contour plot. So the reactants are here, right? This reacts to form FH plus H. So the reactants are here. They have a fixed HH bond length. But as you go to the right, you're basically decreasing the distance from F to one of the H's. And so this is drawn, I mean, in general, this is a three-dimensional system, right? 3n minus 6 is 3. So this is drawn for theta equals 180 degrees. So just only for like head-on reaction, right? So the geometry is like this. Okay, and so this distance is R FH, this distance is R HH. Okay, so as you go in this direction, you approach a barrier, a transition state, right? And then you go over the barrier, and then you end up with a short FH distance, and as you go to the products, basically the HH distance increases, right? The hydrogen goes away, this hydrogen stays close to the fluorine. Okay? And you can kind of imagine, if this is the shape of the potential energy surface, right, then as you come in like this, right, when you go over this barrier, you're going to fall down to the other side, right? And so you're going to get a kinetic energy kick in this direction. And if you just sort of plot, a trajectory, what you would expect the molecule to do if it does that, it's going to fall down this energy hill, and then it's going to have go backwards and forwards in this direction. Well, what kind of motion does that correspond to on this diagram? That's motion back and forth along this RFH direction. So you form this FH product, and then what's happening? Yeah, it's vibrating, right? So this is an early transition state, and it leads to this vibration of the FH product, right? And this is what we talked about when we introduced this reaction, was this reaction leads to a high amount of vibrational excitation, and it actually leads to more product in vibrationally excited states than in the ground states. And this is the reason. You can deduce this if you know what the potential energy surface looks like. Okay? So just really quickly, I'll use the last few minutes to talk a little bit about classical trajectories. And then next time we'll talk about semi-classical trajectories, and we'll talk about energy exchange mechanisms. Okay, so if you have a potential energy surface, the easiest thing that you can do with that to solve for the nuclear motions is use classical mechanics. So you can do a trajectory calculation by classical mechanics. And this is conceptually not so difficult to understand. If you let k be an index for the number for the nuclei, and we're going to let I be either 1, 2, or 3, and that's going to be an index for the Cartesian coordinate, x, y, z. Right? I equals 1 means it's the x coordinate, I equals 2 means it's the y coordinate, and so forth. Okay, then Newton's equations of motion would just tell us that the rate of change in the momentum for the kth atom along the ith Cartesian direction, it's just going to equal, it's minus the partial derivative of the potential energy, right, with respect to that coordinate. Right, so P means momentum, Q means position. Okay, and then the rate of change in the momentum, or in the position rather, I should say, is just the momentum divided by the mass. Okay? So, given V Pik at t equals 0 and Q ik at t equals 0, you can numerically integrate to obtain Qik of t, right? So this gives you the motion of the nuclei as a function of time. And in principle, you could numerically integrate these differential equations using exactly the same methods that we applied in our kinetics course, where we used the Runge-Kutta method to integrate the concentration as a function of time, given the equation for relating the rate of change, right, to the concentrations, right? Except now we're relating the rate of change in momentum and position to the current value of position and momentum, and to the derivatives of the potential energy sources. Yeah?
Is that second equation the derivative time by derivative of time?
Oh, sorry, dt. I have an extra t.
Oh,
This is just
the
speed equals momentum over mass.
Oh, yes.
Okay, I think that's all the time we have. So next time we'll talk about Polanyi rules, and we'll talk about semi-classical treatment. And next time I'll make sure my laptop